Okay, so this is lesson 3.1, and we are going to be talking about rate of change. We are going to start going over the class assignment. And in the class assignment, we are going to be first looking at the definition of rate. So it says a rate is a ratio that compares two quantities. By rate of change, we mean a rate that compares the change in one quantity to the change in another. So for example, when we're talking speed, a speed like 88 miles per hour qualifies because you can write it as a rate. So we have 88 miles per 1 hour. This is exactly what this means. And because we're comparing two measures, specific measures, quantities, that's considered a rate of change. So the word equivalent in math is one that's important because it means when we have two rates that are equal. So for example, in question 1, it says if you make $100 a day for doing a certain job, how much money would you make in a 5-day work week? Well, if you make $100 in 1 day, and I want to know how much am I going to make in 5 days, to go from 1 day to 5 days, we have to multiply by 5. So 100 times 5 makes $500. So the question number 2 says, are these two rates equivalent? $100 per day and $500 per 5 days. Are they equivalent? Yes, they are, because they both describe the same relationship between the number of days worked and the amount of money earned. Also, if we take the 500 per 5 days and we reduce that fraction by dividing both the numerator and denominator by 5, it would take us down to 100 per 1. So they are the same and equivalent rates. Okay, question number 2 demonstrates a useful fact about rates of change. They can be scaled up or scaled down. So that means that I can take a rate and I can make the rate smaller by using division, or I can find an equivalent rate that has bigger values by multiplying. So question 3, write a fraction equivalent to 60 miles per 4 hours. And they specifically are asking to have a 2 in the denominator. Now, if they want a 2 in the denominator, they're talking hours. So they want to know how many miles are going to be traveled in 2 hours. Well, to get a 2 in the denominator, I have to turn a 4 into a 2. So to turn a 4 into a 2, we have to divide both the numerator and denominator by 2. So 60 divided by 2 is 30. 4 divided by 2 is 2. Means 30 miles per 2 hours, and that's equivalent to 60 miles per 4 hours. All right, write 60 miles per 4 hours that has a 1 in the denominator. So to make it have a 1 in the denominator, I'm going to do divide by 4. 4 divided by 4 is 1. 60 divided by 4 is 12. Now, this is an important rate because anytime you have a 1 in the denominator, that is a unit rate per 1. Anytime there's a 1 in the denominator, it will be called a unit rate, and that is very important. Now, write the fraction equivalent to $320 per 4 days that has a 10 in the denominator. This one is tricky because in example 3 and 4, I was able to use one division to turn it into the denominator that we want. But I cannot turn a 4 into a 10 using either multiplication or division, because 4 times 2 is 8 and 4 times 3 is 10. So 10 is right in the middle. So in order to do this, we have to do 2 different operations. I'm first going to turn $320 per 4 days into a unit rate, meaning I want to get a 1 in the denominator. So I'm going to divide both by 4, which gave me $80 per 1 day. Now, once I have a 1 in the denominator, I can really turn it into any number I want. So I'm going to multiply both by 10, which gave me $800 per 10 days. Question 6 is going to use the same thing. So it says a bicyclist is pedaling 40 miles in 3 hours. I want to know another one is pedaling 50 miles in 4 hours. Who is faster? So I'm going to turn both of them into the same denominator, because when we're comparing, I need them both to have the exact same denominator in order to see which one really is faster. So I'm going to multiply the first fraction by 4, I'm multiplying the second fraction by 3, and then we get these 2 answers, 160 miles per 12 hours and 150 miles per 12 hours. Well, which one do you think is faster? The first one, because it travels a further distance in the same amount of time. Okay. Now, questions 7 and 8, we're going to use this table over here, and which is using this paragraph. So it says most experienced runners get to a point where they can comfortably jog long distance at a consistent pace. This pace is another way to say rate of change, because speed is the rate at which distance changes compared to time. So one runner jogs around a 400-meter track in 2 meters. So let's use that number. So for every blank minutes, the runner jogs blank meters. So for every 2 minutes, the runner jogs 400 meters. Now using that information, I completed this table. So time is increasing by 2, distance is increasing by 400. Okay, so we're just adding the same number to each column every single time. Now, question number 9, it says, notice the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates what type of growth we use. So this is constant, right? It's always increasing by 400. The time was always increasing by 2, meaning that this is a linear pattern, linear growth, because we are using add, addition, or subtraction. And this one's always addition, but this would also be linear if we were doing subtraction as well. So write the runner's rate as a fraction using meters in the numerator. Well, he's traveling 400 meters per 2 minutes. Can we write this as a unit rate? Well, to get a unit rate, we have to have a 1 in the denominator. So I'm going to take this 2, divide it by 2, takes me down to 1 minute. 200 meters per 1 minute is equivalent to 400 meters in 2 minutes. Now, question 12 is bringing us back to unit 2, where we had to use dimensional analysis. So it says they want us to convert the rate from question 11 to meters per second. So to go from meters per minute, meters is going to stay the same. The only thing I have to convert is minutes into seconds. So that's where I got this from, 1 minute per 60 seconds. And remember, I had to put minutes on top because I had a minutes in the bottom here, so we had to put minutes on the top so they would cancel. Multiply across, 200 times 1 is 200. 1 times 60 is 60. Now divide. 200 divided by 60 gives me 3.33 meters per second. What distance will the runner cover in 40 minutes? Well, this is asking me for minutes, so I'm not going to use the one we just did conversion for. I need to use the rate of 200 meters per 1 minute, multiply it by 40. 200 times 40 is 8,000 meters. What distance will they cover in 40 seconds? Well, now it's asking for seconds, so I'm going to use the answer we got from number 12, 3.33 meters per 1 second, multiplied by 40 gives me 33.2 meters. And a formula that you can use to calculate this is distance is equal to speed times time. The formula will always work. So we took the speed, 3.33, multiply it by time, 40 seconds gave me my answer. All right, what would the runner's total time be for a 10K race? Well, we know 10 kilometers. We have to use the chart that we were given in chapter 2. We know that there's 1,000 meters in 1 kilometer. And I also know that there's 1 minute, he can travel 200 meters. Now we have to be careful of where units go. So because 10 kilometers is on the top here, we had to put meters in the top and kilometers in the bottom for the first conversion. Now, because meters is in the top, I had to put 200 meters in the denominator, so we had to flip that rate, okay? Just be careful of that. And then I multiplied all the numerators across. 10 times 1,000 gave me 10,000, and 1 times 200 gave me 200. Divide the 2, and you get 50 minutes. All right, so that is the end of the classwork. Go over it. If you have any questions, make sure you sign in to my office hours when I'll be doing face-to-face time, so you can ask me any questions on it. And before you go on to the next video with the group work, you should try those examples on your own, because that'll give you an idea if you understand what we just did, and then use the video to check your answers, okay?